All right. Last class till Tuesday. We have lab tomorrow, but this is the last lecture. Um, I'm going to finish the example problem we were doing, and then I have some problems for you to work on. Um, Before I get into that, anybody have any homework questions you want me to go over? Yeah. Number 6. Do you happen to have it with you or anybody? Okay. So first question is 2D particle kinematics. Number 6. So this is the one where someone's shooting a basketball. Um, and we know that at the spot that it's shot from, it's shot at an angle of 60 degrees above the horizontal. And we know the distance from the horizontal distance from the shot to the basket. That is 15 feet. That's 3 free throw distance. What is that? Anyone remember? 4.578? 4.57 meters, and then the height is 10 feet. And that is 3.05 meters. And the initial velocity, so it's shot with a speed of 7.8 meters per second. And we want to know what height it's shot from. That would be an interesting basketball strategy to just get really good at shooting with one angle and one speed and then just shoot from different heights. I'm not sure it's a very good strategy, but so what we're looking for is this, we want to figure out the height that it's shot from. That's part A. And then part B is we want the displacement vector from, where it's shot from, to the highest point. Okay, well, I'm going to draw the coordinate system and the coordinate system orientation on the picture, and then we'll think about what times we want to choose. I said before, I pretty much just always make the same choice of where I put the origin. I put the origin on the lowest point of the problem, that's the ground in this case, with the y-axis pointing up and the x-axis horizontal. Putting the origin on the ground in this problem also has the advantage of So when we come up with, since it deals with things in terms of heights and stuff, the y position is just going to represent the height at any instant. Okay, and for part A, at what instant do we have information and what instant are we looking for information? Well, we have information when it's at the basket. We have some information when it's shot. We're looking for information when it's shot. And so the choices of time equals 0 and time t are pretty straightforward. Time equals 0 is when it's released. Time t is when it reaches the basket. And now we can think about the variables. So t, a, position at time 0, position at time t, velocity at time 0, and velocity at time t. We don't know how long it takes to get to the basket. We do know the acceleration, since it's a free fall problem. The position at time 0, we know that px is equal to 0, and we're looking for py. This is p0x, I guess. So we know p0x, and we're looking for p0y. That's sort of an unusual variable for us to look for, but that's what we want here. And for this problem, we actually know the position at time t. Usually those are, more often those are switched. But in this case, the x position is positive 4.57, and the y position is positive 3.05. And then to find the initial velocity, here's our coordinate system. Our initial velocity vector makes an angle of 60 degrees with the horizontal. And so that vector is 7.8, that's the speed, times the cosine and sine of 60 degrees. Can someone calculate that? 3.9 and 6.75. And then the velocity at time t, we don't know. Although it's true that the x component of the velocity is going to stay constant through the whole thing. All right, so now we're looking for an equation that'll work with these to let us solve for p0y. We know it has to be one of the 3 y equations. We don't know time, so that eliminates 2 of them. So the only possibility that could possibly work is 2ay times the quantity py minus p0y, that equation. So we can think about whether that would work, and it won't because we don't know the y component of the velocity at time t. Okay, so no equation works. So what's the next step? Yeah, so let's try to solve for t. And then once we have t, maybe there'll be an equation that'll work for p0y. Okay, so what equation is going to work here? It looks like, so most often with these kind of problems, we'll use a y equation to solve for t and then plug it into an x equation. that's another way that this problem is sort of backwards from what we're used to. The one that's going to work in this case is Px is equal to P0x plus V0xt plus 1/2 ax t squared. Ax is 0, so this goes away. And so what we have is 4.57 is equal to 0 plus 3.9t. What's 4.57 divided by 3.9? 1.17 seconds. So now that gives us one more thing that we know. And now that'll let us use this equation. Py is equal to P0y plus V0yt plus 1/2 ayt squared. So 3.05 is equal to P0y, that's what we're trying to find, plus 6.75 times 1.17 minus 4.905 times 1.17 squared. And what do you get for P0y? The number 1.87 sticks in my head. I'm going to guess it's that, but I certainly didn't just do the math in my head. This isn't a very good strategy for shooting basketballs, but this is what you have to do if you're ever setting up a pitching machine. You know, it's got to be on the pitching mound. You know the distance from home plate. The thing is just going to go its own speed and its own angle, and you're just trying to adjust it to make it find the strike zone. And then the second part of this is we want to find the displacement from where it's shot, which now we know, to the highest point. So for part B, we can still use the same origin and coordinate system. And we can still use the same time equals 0 instant. But now our time t has to be when it reaches the highest point. So now we have to go through again and think about which of these stays the same, which of them changes. T, acceleration, P0, P, V0, V. Well, we figured out the time that it took for it to hit the rim, but that's not the time that it takes to get to its highest point. So now we don't know this again. Okay. It's still in free fall, so acceleration is still 0, negative 9.81. At time equals 0, the position is 0 for x, and then what we just calculated, 1.87 for y. We don't know anything about the position vector at time t, but we are trying to find, well, actually, we're trying to find both of these. So this is what we're looking for, both components of that vector. Because once we have the components of that vector, we can do the subtraction to find the displacement. The velocity at time t, we know that that's 3.9, 6.75. And we're going to keep assuming that we don't know anything about the x component of the velocity, even though it stays the same. But we are going to have to specify that Vy is equal to 0. That's how we're going to specify the highest point. Okay, so can we solve for either of these without finding the time? Yeah, it looks like we can use this equation. 2ay times the quantity py minus p0y is equal to vy squared minus v0y squared. That says negative 19.62 times the quantity py minus 1.87 is equal to 0 squared minus 6.75 squared. And so py is equal to negative 6.75 squared plus 19.62 times 1.87 nope, that's minus, divided by negative 19.62. Can someone calculate that? 4.1, I'll just leave it at 4.19 meters. So that's the height, the highest point of the flight. So in this picture, that's the height here. Okay. We don't know the horizontal position either, so now we have to solve for that. And now we're stuck without knowing the time. So turns out we had to solve for the time anyways. So nothing works for px, so find t. The easiest way to do that is to use this equation. Vy is equal to v0y plus ayt. So 0 is equal to 6.75 minus 9.81 t. And so t is 6.75 divided by 9.81. What do you get for that? 0.69. And now that we know that, we can use the x position equation. So px is equal to p0x plus v0x times t plus 1/2 ax t squared. So px is equal to 0 plus 3.9 times 0.69. Ax is 0, so plus 0. And what do you get for this? 2.69. 2.69, I'll leave it like that, meters. And so if we put these together, the position at the highest point is 2.69 for x, and then what we calculated, 4.19 for y. It doesn't ask for that, it asks for the displacement, but the displacement is just the position at time t minus the position at time 0. So that's 2.69, 4.19 minus the initial position was 0, 1.87. And so the x component of the displacement is 2.69. And what's the y component? Okay, 2.32, and that's in meters. And what that means is if you draw a vector from where it's shot, the point where it's shot, to where it is at its highest point, it looks like that, light blue. And if I had drawn this picture really carefully, known where all the points were and stuff, the components of that blue vector would be what we just calculated. Any questions about that one? Any other homework questions you want to see? Okay, so this is the one where a car is moving and an object is dropped from the car. So the car is moving this way with an initial speed v. And an object is dropped from the car from a height h. How far does the object travel horizontally before it hits the ground? Okay, so here's the car. And it's going this way with the speed v. And an object is dropped from here. And when the object is released, it's going to have the velocity of the thing that it's dropped from. So it's going to be moving horizontally with the speed v. And it's going to travel along a parabolic path because it's in free fall. And we're looking for the horizontal distance here. and this distance is h. Okay, well, I'm going to put the origin on the ground right beneath where it's dropped. So x-axis is horizontal, y-axis is up. The places where we have information are, we know some stuff about when the object's released, and we know some stuff about when it hits the ground, and we're trying to find information about when it hits the ground. So those have to be the two instants. So time equals 0 has to be the instant when it's released. Time t has to be when it hits the ground. And now we can start thinking about what we know and what we're trying to find. So there's t, a, p0, p, v0, v. You know, normally in these problems, instead of having things given in terms of constants, we have numbers for things. In this problem, we're going to have to figure things out in terms of that h and that v. And so since we're already doing things symbolically, I'm going to think of gravity as as just g down. G is 9.81. Okay. You could use that number, and then the only values left would, you know, the only constants that you have left in your equations would be h and v, but I'm going to use that g too. Okay, we don't know how long it takes to hit the ground. We know that it's in free fall, so the acceleration is 0, negative g. At the instant that it's released, the position is 0 for x, positive h for y. We're trying to find px, and py we know is 0 because it hits the ground. And the initial velocity, what do we know about that? Well, if this is the coordinate system, r's velocity is horizontal, and so that's the object's velocity at the instant it's released. And so if you have an object moving in the positive x direction with the speed of v, then that velocity vector is just going to be positive v for x, 0 for y. And we'll assume we don't know anything about velocity at time t. Okay, so is there an equation that works? No. And so we're going to try solving for t and then see if we can use that. To find t, we can use the y position equation. So py is equal to p0y plus v0y t plus 1/2 ay t squared. Py is 0, p0y is h, v0y is 0, and this is negative g over 2 t squared. And so t is equal to 2h over g square root. And when you take that square root, you get a plus or a minus. Which one of these do we want? We want the plus because it's time. And now we can plug that into the x position equation. So the x position equation says px is equal to p0x plus v0x t plus 1/2 ax t squared. So px is equal to 0 plus, this is just our v, and our t is square root of 2h over g. Ax is 0. So our final answer is that px is equal to v times the square root of 2h over g. Any questions about that one? Any other homework questions you want to see? Okay. Well, let's finish the example that I started last time. So the example from yesterday we had a horizontal ground and a wheel rolling without slipping. We were given that the radius of the wheel is 1/2 meter. The center point I called C. The contact point at the bottom I called B. The top point I called T. And we were given that the angular velocity and angular acceleration were both counterclockwise. So it was 2 radians per second. And then the angular acceleration was 10 radians per second squared. And the equations that we used were for rolling without slipping. We know that the velocity of the center is all in the x direction, and it's equal to negative omega r 0. And we know that the acceleration of the center is all in the x direction, and that's negative alpha r 0. And then we use 2 relative motion equations. So I'll just write those as VAC is equal to VAB plus VBC, and then the acceleration version. And what we figured out so far is that VC is negative 10 meters per second. and AC is -50 meters per second squared. And then we used relative motion to calculate that the velocity at the top is -20. That velocity is always going to be twice the velocity of the center. And so now we want to calculate the acceleration of the top and the velocity and acceleration of the bottom. Okay, well, to calculate the acceleration of the top, the process is about the same as calculating the velocity of the top. We're going to use the relative motion equation that says acceleration of the top relative to the ground is equal to acceleration of the top relative to the center plus the acceleration of the center relative to the ground. This one is this. And this one is circular motion, assuming that the center is fixed. So ignoring the motion of the center and just doing the circular motion. All right, so to calculate the acceleration of the top relative to the center, let's think about that circular motion. So we have this thing that's moving this way at 2 radians per second and 10 radians per second squared. So we know the velocity direction is this way. What direction is the tangential acceleration? The same as the velocity, because you can think of it as it's speeding up because the two angular quantities are the same direction, or you can just recognize that if the angular acceleration is this way, the tangential acceleration has to be tangent to the circle in that direction. Okay, so this is the tangential acceleration. The centripetal is always toward the center. And now we can calculate the magnitudes of those. The magnitude of the tangential acceleration is the absolute value of the angular acceleration times r. So that's 10 times 0.5. So 5 meters per second squared. That's in the negative x direction. So the tangential acceleration vector is -5, 0. The magnitude of the centripetal acceleration is omega squared times r. So that's 2 squared times 0.5. So 2 meters per second squared. That's in the negative y direction. So the centripetal acceleration is 0, -2 meters per second squared. And now we can put those together and we get that the acceleration of the top relative to the center, okay, that's the one that we're getting with circular motion, is equal to -5, -2 meters per second squared. So that means that the acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center, what we have here, plus the acceleration of the center relative to the ground. That's -5, and you get -10, -2. Any questions about that? Okay, so now we're going to do the same thing for the bottom. It's going to be the exact same approach. It's just that where at the top, we'll see when we use, yes? I plugged in -5, 0 for, yeah. Okay, so at the top, we saw that when we use the relative motion equation, the acceleration and velocity of the center and the acceleration and velocity from the circular motion were in the same direction, so they added, and that's why we got that double size on the x components of these things. We're going to see when we use relative motion for that bottom point, they're opposite directions, and so they offset each other. And what we're going to see is that the horizontal velocity and the horizontal part of the acceleration of that point are 0 at the bottom, which makes sense if you think about what it means for the wheel not to slip on the ground. If the point in contact with the ground doesn't have the same horizontal velocity and acceleration, that means that the wheel is slipping at that instant, okay? So at that instant, the horizontal part of the acceleration and the velocity have to be 0, and that's what we're going to see. So right at that instant, it comes to a rest and then starts moving again. Okay? So now the bottom. For the velocity, we're going to use velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. We already have this. And this one, the velocity of B, assuming that C is not moving, is circular motion. Okay, so let's think about the circular motion. It's going this way, that's the angular velocity and the angular acceleration. And so at this point D, the velocity has to be this way. Which direction is the tangential acceleration? Same. And the centripetal is toward the center. So we know the directions. Now we can figure out the magnitude. The magnitude of the tangential acceleration is absolute value of alpha times r. So that's 5. It's in the positive x direction, so the tangential acceleration vector is positive 5, 0. The centripetal acceleration magnitude is omega squared times r. So that's 2 squared times 0.5, so 2. And we know from this picture that that's in the positive y direction. So the centripetal acceleration is 0.2 meters per second squared. And so the acceleration of B, assuming that the center is fixed relative to C, is 5.2. Okay, so we'll use that in a second. And let's figure out the velocity vector too. The magnitude of the velocity is the absolute value of omega times r. So that's 2 times 1/2, so 1. And the velocity is in the positive x direction. So the velocity vector of B relative to C is 0, 1. Nope, 1, 0. And now all we have to do is put those together with the relative motion equations. So I'll do velocity first. So the velocity of the bottom relative to the ground is the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. That's 1, 0 plus velocity of the center relative to the ground. We got that last time, is -1, 0. And so just at that instant, when the object is at the ground, the velocity is 0. And then the acceleration of B relative to the ground is the acceleration of B relative to the center plus the acceleration of the center relative to the ground. Acceleration of B relative to the center is +5, +2. Last time we got that the acceleration of the center is -5, 0. And so the acceleration of the bottom is just 0.2 meters per second squared. So at that bottom point, the velocity is 0. It's instantaneously at rest. And the horizontal part of the acceleration is 0. Those are the things that are required for the bottom not to slip against the ground. Okay, and that's always the case with rolling without slipping. Any questions? Okay, see you in lab tomorrow.